It's Monday. And then so for me, that means it's Big Business Monday, where I essentially focus more on business related items. And so if you're just joining me from over the weekend, generally research and academic research doesn't get published over the weekend. So that's where I do more of my experimental research, release my experimental models, etc. During the week, I tend to focus on different areas. Beginning of the week, I tend to focus on big business. My background, people have asked, so for about the last 10 years or so, I have a lot of experience consulting, specifically with regards towards enterprise businesses and enterprise systems. Very specifically within that, I have a lot of experience with integrations overall, and especially connecting large systems together, so CRMs, ERPs, etc. If you're a Fortune 50, there's a very large chance that I've seen the back end of your systems personally, know exactly what they look like. Or, I mean, either I've seen them personally or I can tell you exactly what they look like, kind of is the bottom line within that. And then within that, a large concept within especially enterprise organizations is federated systems. And so I first ran into federated systems about, let's call it 15 years ago or so, with a large oil and gas manufacturer. And within their Salesforce or instance and organization, right? And I think Salesforce is a good framing and example for this. If you've ever used a system like Salesforce, any sort of cloud-based ERP, cloud-based CRM, etc., you're very familiar with this architecture on the front end. You just probably don't know what it looks like on the back end with a diagram like this, right? And then so essentially on the front end, you get served your user interface. So like all of your systems join together. And then so whether that be like an individual program, like your docs, your spreadsheets, your email, etc., it's all served to you in a single UI, and you only see your information, right? But let's use like Salesforce as an example. You'd be readily aware that you're not the only company that utilizes Salesforce. And then so on the back end, perhaps it's not every single company gets provisioned their own individual server within Salesforce, right? That'd be very expensive for Salesforce. So your data likely sits on a server and is shared with lots of other companies' data, but it never touches the individual company's data on the back end. Even though it's on the same physical server, there's lots of separation layers on the, like all of these separation layers between your data and any other data, right? And then these separation layers work like containers, and then so it's kind of a containerized system and like a hierarchy of containers, right? And then so it's where are you at on the hierarchy of containers? And I first saw this again with it's like manufacturing companies, and then they have distributors that are under the manufacturing companies, and then so the manufacturing company would want to be at the top of this layer, and then be able to see all of the companies, but then the individual distributors would see only their individual data, etc. And that's kind of a big like concept overall for this. If you want like a more simplistic example of this architecture, we can look at it here, right? Where you have a server and then you have database 1, 2, and 3, which all sit on the same server and are all connected to the same server. And then what you see is that there's a bunch of encryption and aggregation and different types of layers that sit in between these, right? Another common example, and like I see this more and more internally with like a kind of like SMBs and larger with regards towards like PIIN information, right? So where you have a database 1, database 2, database 3, and then each one of those, let's say database 1 and 2 don't contain any PII, database 3 does, and then so people have like very few people have access to the server itself, to server A, and then so the aggregation of data on server A, and then the only time that like data from 1, 2, and 1 and 2 get blended with 3 is on server A and nowhere else. And then so kind of that like restricted flow of data and information and being able to segregate and aggregate the data and is big on the back end within these systems, especially for security type of purposes. But so why are we talking about this on an AI channel? Very specifically, we're talking about this because this research paper, personalized federated learning via learning dynamic graphs. Essentially, this is a model that they put out for federated learning for LLM models and for AI models overall, right? I'll show you an instance of utilizing it for both a CNN and as well as for an LLM specifically. And then they lay out the framework, and I'll go over the framework here in the code, but they don't provide you any sort of the code within the framework. So what I like to do on this channel is, this is good theory, and they give you all of the framework and the theory here, but let's put it into practice, right? So First example, let's look at a full example of a GAT, which is a graph attention network in this particular instance, and see what exactly that works, right? So that and how that works, because this is all predicated off of this graph attention network structure. And then this is going to be, in this first example, the only time where I'm actually fully building out the GAT. And then I'm building out utilizing synthetic graphs and synthetic data, which is why I'm only building it out once in this instance, right? In the other experiments that I'm doing, it wouldn't be actually useful for synthetic graphs and synthetic data as opposed to just passing it. So within this, what we see here is, so we have our synthetic graph creation, and then so I'm just giving all of the instructions for the data, right? It's simple labels. So predictions and then numbers for the labels and then 2 colors. And then this is a very simple neural network, right? And very simple layer of the graph attention network itself. And then so within the graph attention network, within the graph itself, that's where the attention weights come in, right? That's why it's a graph attention network. This is a neural network built around graphs and graph structures. And if that's kind of a foreign concept to you, I've shown on this channel lots of different instances of shaping neural networks from way different types of architectures. You can shape swarm algorithms, genetic algorithms, etc., into neural networks. And then so shaping a graph structure into the neural network is actually not very fun at all. And it's actually, it's inspired because the models do learn off of graph-like structures. It's my problem with, generally speaking, as putting them into a graph attention network is that you want the graph to be more fluid and less linear than a typical graph overall, but you can. And so that's what we're doing here. And then so you have the full network here, and then we have our training function, and then just the visualization and the demo that I'm here for you, right? And then so we can see here that it trains, and then so in this instance I'm training it for 100 epochs, and it ends at 80% accuracy. If I trained it for, let's say, about 200 epochs, I think would be more reasonable in this instance, and we would probably get it up to, let's say, 98% accuracy or so. Generally, even with a graph neural network, you're not going to get or want 100% accuracy, because then it's overfitting, and graph neural networks can definitely overfit as well. Right? So that's a thing that you want to look out for, and make sure that you're not over tuning the model overall, and your expectation is that you're not going to have 100% accuracy even with the graph layers, right? You don't want to train it to 100% every single time, generally speaking. It's going to be high, 98, 99, but generally speaking, 100% is overfitting. And then we move down to our example of actually utilizing this, and so combining the graph neural network plus this concept of federated learning that I started the video off with and I've been talking about. And let's put that to real-world use in a CNN, right? So first of all, what I'm doing is I'm building out the CNN model, and then so from here, what you're going to see is this a client wrapper, right? And then so this is going to be all of this down to here is just this is all a client wrapper, right? And then so this class right here is the framework from the paper. Right? This is all of the framework that they're putting in here. This is what it is, right? And this is federated learning and a federated distributed system when it comes to neural networks, essentially. So you're just wrapping the individualized instance in a client wrapper. So you're essentially creating that individualized separated space within the neural network itself, right? And that's what this does, right? It's so when you run through this and we look through the whole code, right? So then you have your server class, which data gets aggregated on the server class. So it's replicating this structure inside of the neural network. Right? It's what is cool to me about this approach overall. And then this is just a sample training loop here. And then we can see this is sample data, right? And then so you can see this is how it would work out, right? And then so in this instance, I have a singular CNN model in this instance. And then I have client 0, client 1, 2, and 3. And then I run, and then each one is training on its own individualized data, has its own individualized optimizer, etc., right? So you can see that the loss would be different the metrics and the performance metrics during training can be different while I'm training all three of these individualized models. And then so again, if you're like say like manufacturer distributor type style, and you're I think more and more companies are going to be wanting to do training like this, right? So this gives you the simple framework there. And then this is an example of doing it with an LLM model specifically, right? And then so I'm flat out using a toy model for the LLM model. I'm not trying to do anything crazy here. I'm just trying to show that it works. You would just essentially replace this with your actual LLM model. But again, same thing, right? Client wrapper, like this is like the client wrapper is what's important here because that's where the framework is. And then it's that same. And then you have the same thing for your GAT, right? It's your graph neural network is going to be the same overall. And then your server. And then I'm pointing out here, if you do utilize this code, like the one thing that you want to do in these instances is like, first of all, like put in a real LM model. And then second, you want to do this, like this update GAT function. You can see I'm passing it right now. So like my code isn't actually updating the graph neural network in this instance because like that's why I showed you the first one, because I'm not trying to build it out for just simple demo purposes in every single one of these instances, right? And have it run through. If you don't if you're building and training a graph neural network, it's a lot to build it and train it from the beginning, right? It's an intense project to take on overall, and so I'm not trying to just do that just honestly for simulation purposes. And then so we go through, and then we have, again, I'm just simulating the models in this instance, and then we would go through again, and this is the same concept but with an LLM model, right? And then I'm surprised that this is actually like registering anything at all as far as accuracy, even 0.01, right? So it's like it's guessing something, which is kind of cool and interesting with my demo model here. But same concept, right? So you've got like 5 epochs in this instance, and then you've got like 3 different models that you're training across 5 different epochs. And then this is just more examples of like the like building out. So within this architecture, they give out like some different like frameworks to utilize within it, and how to like actually like structure out their like individualized components of the framework. And then so that's what I do here. So like this is like training for multiple individual clients, like utilizing this full framework, right? So let's say that we have essentially the MLP model is like would be the server in this instance, right? And then so it rolls up to that, and then the individual, like so this CNN model, and then we could have multiple CNN. Like this CNN model would be broken up into the individual databases. So this CNN model could be database 1, 2, and 3, etc., right? And it'd be representative of that. Then we also have our transformer model. So showcasing like you can have like exactly how you would have like an actual federated system here, right? Where I can have like Excel and SQL and web services and XML and like etc. I'm trying to show that and showcase that here, that here's both the CNN as well as the transformer model. And then essentially within that, we create this additional client class, right? And then this client class is what separates, and it's the client class is that hierarchical blocks really is how that structure ends up working out. And then of course we have our GAT layer, and then so we're like this is a the parameter projector is when we're combining parameters and in this instance from different systems, right? From like a CNN compared to a transformer, etc. And then so we need layers to blend that in, and then so we blend that in a few places here. Again, this is the only placeholder here, this update GAT, but the update GAT is a placeholder, and then we have the main training loop, and then we get essentially. In this instance, again, it's kind of just showcasing the same thing and what you would expect here, right? And then so we can see like we can get vast. Like what I want to showcase within in this is like a test like this, right? Where it's like we could have 2 like client models. Like one is getting 62%, one is getting 52%, which is decent. It's on its way there, but then that third one's 17%, right? So we would have like in this instance 2 models training really, really well, and then 1 model that we would need to go back and do some work on, which can happen under this framework. And then so highlighting that out. And then in that last cell here, I just took like literally every single concept that they see, because they give you these individual algorithms, like algorithm 1, 2, and 3. So I plug in their algorithms here, and then get, like, here's their full bells and whistles framework, right? So all based off of the paper very specifically. So they have personalized layers. They have some work here on the client layer that I give you some updates to. And then they have this. So their major thing in the paper that I like is this cluster manager. And then so what they like this particular algorithm does is it groups and it tells the model to group and cluster client data together into like create a cluster of client data. Right. And then so like you say, like going back to this, right, you have database A1, 2, and 3. It's kind of telling the model to cluster data in this way. It's giving the model more instruction on exactly like you should actually be clustering your weights and creating your weights in this context, right? Like create an area and a space within your neural network for database 1, and then create a different space and a different cluster area for database 2, etc. So it's really cool addition there, and I really like that. And then everything else is the same there, but then you have the fed per model for like this is for better like their model for and their algorithm for putting it all together in that unique way, and then dealing with those clusters. And then I have in here some code for meta learning if you want to incorporate that, which would be like updating the graph policy, etc. So very simple to just add that. But then again, this is like what you would get, right? So you have in this instance, it's rolling up to the end model. So how this works is what you get, and this would be beneficial for you as like the person that is like running this, right? Is that you get your global model that's trained. So again, going back to this, pretend server A is LLM model A. Right, and then so LM model A would get still like trained on all like and aggregated to all of this data, and you could that's a toggle that you can turn on and off, highlighting that, right? But you can have it aggregate all of that, and then so your LM model A is like the kind of the grandmaster of all of this data, right? It gets to tune, but then it's fine-tuned on all of that aggregate data, but then it's also fine-tuned on all of the aggregate data in a way where it's creating this database-like structure. And you're building out more and more of a database structure of your model, like the more that you build it out, right? And so it's on each one of these testings, you're training it on a global level, and then you're training it on the individual client level. And then you're just tracking both of those metrics, right? Like how well is the global model doing, and then how well would the client model do, which are two different metrics overall. Really cool in this framework. So as far as federal learning, this is the first concept that I've seen overall for like AI models within this. So just highlighting this and putting it out, and I wanted to make a video here. So again, my code is MIT licensed. I'll leave a link to both the code and the paper. If you like this type of content, please like and subscribe. Thank you very much.